I'm smiling because I'm going to perform a magic trick right here. In this video, I want to show you how to multiply a 3 by 3 by 3 matrix with a 3 by 3 matrix. I assume that you're already familiar with how do you multiply a 3 by 3 matrix with, let's say, a 3 by 1 matrix. You take the first row, make it a column, and then multiply element by element, add those up like this. You're very familiar with it. And if you multiply this particular identity matrix with any 3 by 1 matrix, you would get the same 3 by 1 matrix. Now for the magic trick and for the main first question, what would a 3 by 3 by 3 matrix look like? Of course it would look like a cube. And for the magic trick now, ta-da! So this is what it would look like. You can imagine, I hope that some of you try to guess what it looked like. The column, there's only one diagonal, the green ones are the ones and then the white ones are zeros. So you have most of them are zeros, and then only along the diagonal where the row equal to height equal to row equal to column equal to height is where the row equal to column equal to height. So you have 1 1 1, you have 1 1 1 2 2 2 and 3 3 3, and they are all 1 and rest of them are 0. Now if you multiply something this, which is the identity matrix in third order, what we will start calling this the third order. This is the second order matrix, this right here. This is the first order system, but this is a third order thing. And if you multiply that with a second a flat matrix, you would get a flat matrix again. And see, I hesitate calling this a 3D matrix and a 2D matrix, even though the title and everything I say that, because the dimension really is how many rows and columns you have. So this is third dimension because you have 3 rows and 3 columns. If we have a fourth one, then we have a 4-dimensional but second order, because it's still a 2D matrix. 2D, okay fine, I'll call 2D matrices like this, who are flat, who have rows and columns and no height. Okay, now for a good example of what a 3 by 3 by 3 matrix we all use is called the, don't be scared, I will explain it, Levi-Civita symbol. And you have used it whenever you calculated determinants, cross products or curls. Determinants, I hope that most of you would have, I don't hope, but most of you would have known how to calculate determinants, at least of 2 by 2 matrices. Okay, now give me a second. Now this is an identity matrix in 2 dimensions and second order. How is it defined? It's 1 when I equal to j, so this is I and this is j. So when 1 equal to 1, it's 1. When 1 and 2, when we are talking about the element which is at here and this place, which is denoted by 1 comma 2. So let's define this symbol delta here and ij. So delta 1 1, so this is delta 1 1, that's 1. Delta 1 2, that's this one, delta 1 2, that's 0 because I not equal to j, and then we get this matrix. Now the question is, what is the opposite of this matrix? The opposite of this matrix, can you imagine? It's like the Christ and antichrist. The opposite would be, it's defined like this. It's called the Levi-Civita symbol. Now actually I should use a different letter called E here, but for Cartesian coordinates it really doesn't matter. So here it's 1 and 0 and -1. Now the conditions are I and j have to be in a positive order, so in, let's say, an increasing order, and it's 0 when I equal to j, because you know it's the opposite of this, anti this, and when it's the order is opposite, then we have -1. So for example, when you're talking about uh, this is e epsilon of 1 1, that falls under here because I equal to j, so that's 0, and 2 2 also 0. Now when you're talking about 2 1, then it's 2 1 is the reverse order, so it's -1, and here we have 1 2, which is a positive order, so we have +1, and this is the opposite of that. Now I ask you this, and try to pause the video and work this out yourself. When we have a 3 by 3 identity matrix, what is the corresponding antisymmetric, the arch nemesis of this, like what we have for this, what is it for this? And the definition is again 1 0 minus 1 I j k in a positive order, 0 when I equal to j or j equal to k or k equal to I, and minus 1 when the order is the wrong order. So to give you an idea, when you're talking about now, okay, so this is going to be a 3D matrix, and okay, we are also not talking about this second order matrix. We are talking about the third dimension matrix that I showed you with my magic trick, not this one. So let me remove this one. Okay, so in this case, if we are talking about the first, now okay, again imagine that I'll pull that up, hold on. Now when we have something like this, then okay, I can't do that, so I'll use my cursor. So this one would be 1 1 1, this one would be 1 1 2, and this would be 1 1 3, this would be 1 2 1, 1 2 2, 1 2 3, and this would be 1 3 3. You get the point. And then this is 2 1 1, 2 1 2, 2 1 3, and so on. So this is how this matrix is indexed. Generally they don't show these indices, so you might not have thought this much about this much in college whenever you took this course. Okay, now try to imagine what it would look like in 3D, and I'm going to spoil it in a second. This is how it looks like. The reds are the minus ones and the greens are the plus ones, and you can see that it's the opposite, because here you have a green diagonal and this plane sort of is the opposite of that green diagonal. This is so hard. You get the point. Why don't I just write it down, because we are going to use it anyway. And how would I write down 3D? I'll show you. This is how the ordering goes. So if you have 1 2 3 3 1 2 or 2 3 1, you have plus 1, and you have minus 1 when you have 1 3 2 2 1 3 sorry 2 1 3, yes, and 1 3 2 1. Okay, and now try to, this is how it looks like. You only 6 of the 27 elements, since it's 3 by 3 by 3, are non-zero, rest are 0, and the 6 elements look like this. So if this is the plane, and then it's like it goes like I don't know if you got what I was trying to say. uh, okay, now I will write down the matrix here, but try to work it out, using this, but I will just write it down. So this is the 3D matrix. It's like plane plane plane, and it's actually the negative of this. I think I messed up the sign somewhere here. So the green one here, this one, the red one here, that's supposed to be green and this is supposed to be red. So flip the signs here. Red now means plus 1, and this is the matrix, and you have this plane, that plane, and that plane represented like this. Now here we have I equal to 1, that's that plane, I equal to 2, and I equal to 3. And then you have I equal to 1, j equal to 1, k equal to 1. Get me? And this is I equal to 1, j equal to 3, k equal to 3. So this is 1 3 3. For example, this is 2 2 2. This is 3 1 3. Okay. Now the question is, how do we use this? And I will give you an example of cross products. So you might have heard about, well, you would have learned about the vector product of two vectors. So you have this vector and this vector, and the product is something weird like this, and a conscientious math teacher would complain about how these are vectors, these are scalars, you are putting them in a determinant, which is weird. Now there is actually some interesting thing going on here, which is that I will show you. This cross product can be represented with our Levi-Civita symbol, or the unit antisymmetric matrix in 3 dimensions and third order. And I will show you how you could, what is the mechanism behind this, and of course the goal of the video is to show you how to multiply a cube matrix, a 3D matrix with a 2D matrix. So that will come in handy. And let me pause and write some more stuff down. Now this is the real definition of a vector product or a cross product. This is the matrix that we discussed, the 3D matrix. When I say it quickly, 3D matrix, then I mean like a cube shaped matrix. And now what is this bj and aj and bk? We know that ai or an or whatever is a1, a2, a3 and b1, b2, b3. Then what is this thing? Because you might think that's the dot product, so a1, b1 plus a2, b2 plus a3, b3, but no, this is a 2D matrix or a 3 by 3 matrix. Here, since we have two indices, we calculate the products of each possible product between these two. So we would have here a1 b1, here we would have a2 b1, and then a3 b1. Then you have, well, I'll skip through this, but you get the point. You multiply all the 3 into 3, 9 possibilities, and you put them into this matrix. Okay, so this is the product of this vector and this vector. It's called an outer product, where all the possible multiplications between terms are stored. And now we will multiply that with this matrix, this 3D matrix, the cube matrix that we saw, and then we should get the cross product. Remember that if you go the traditional way, I will quickly write it down. So it goes something like I into a2 b3 minus b2 a3. Why don't I pause again? Now when you multiply this matrix, which has all these possibilities and more, with this cube matrix, you should get this product, which is a vector. It has 3 components, 1, 2 and 3. ijk is just for our Cartesian case, but this is the component 1. This is c1, c2 and c3. Now in case of here, if you put I equal to 1, so c1 equal to epsilon I jk, and then you multiply the first this one with this one. Now if you just take this matrix and then multiply it element by element, you would get a3 b2 minus a2 b3. Like you just take this, put it here, and then multiply each element by each element. So you have 0 0 0 0 multiplying these 3, so you get 0, and the only thing that remains, and then you add everything up, and the only thing that remains is this. Here it's plus 1 and here it's minus 1, so you get a3 b2 minus a2 b3, but we have a2 b3 minus a3 b2. Oh, it should be better written as a3 b2, and the reason is the same as we saw in the previous normal two-dimensional matrix multiplications, where you have, if these two matrices are multiplying, for example, then we take the first row, we make it a column, and then we multiply, and that's when we do that, we're taking a transpose. So we have to take the transpose of this. When we take the transpose, then the whole matrix would the rows will become columns and columns will become rows, so this will become plus 1 and this will become minus 1, and then we have this. And you could check for the rest of it. You have to take the transpose, multiply, or you, in this case, you just flip the signs, and then you would get this product right here when you multiply this cube. So again, to visualize, you have the cube, you have the matrix which is like this, and the cube is like this. You take the first of the cube, then you take the transpose, you multiply element by element, you add it up. You take the second of the cube, take the transpose, multiply it again and add it up, and then you take the third and add it up, and then you have this row, which is the cross product here. You can also use the similar formulas using the epsilon or the Levi-Civita symbols exist for curl and determinant. In fact, the definition of determinant is with this, but then they teach us this whole thing because this is harder to teach to kids. But I hope that you enjoyed this video and this magic trick. I was going to perform more magic tricks, but I thought, wait, no, just stick to one this time. So thank you for watching.